Today we'll be discussing about the chapter Structure of Atom. We'll first talk about the fundamental particles which are constituting the atoms. As we know that the atom is consisting of three fundamental particles. The first one is electron, second is proton, and third one is neutron. If you talk about related to that, the first we'll talk about their masses. The electron is the lightest particle of the atom, which is consisting of 9.1094 into 10 raised to minus 31 kg. That is approximately equals to 0.00054 AMU, which is considered as almost zero atomic mass. The charge of this particular electron is equals to minus 1.602 into 10 raised to minus 19 coulomb, which is nothing but taken as one positive charge. And we already know that electron is being discovered by J.J. Thomson during its discharge tube experiment. But the charge related to the electron is being determined by the Millikan by its oil drop experiment. The proton is having mass of 1.673 into 10 raised to minus 27 kg, which is approximately equals to 1.007 AMU, which is considered as same as the hydrogen atom. The charge related to the proton is taken as plus 1.602 into 10 raised to minus 19 coulomb. So it is considered as 1 unit positive charge. This particular proton has been discovered during the anode ray experiment by the scientist Goldstein. The next thing is a neutron. Neutron being having mass of 1.675 into 10 raised to minus 27 kg, which is almost equals to 1.009 AMU. So this neutron mass is almost same as a proton, which is considered as same as the mass of the hydrogen, where we say there is no charge on the neutron as being discovered by the scientist Chadwick. So these are all, we have the different types of the particles available in the atom. Out of this we say generally the protons and the neutrons are present inside the nucleus and they are contributing to the mass of the atom. So together they are called as nucleons, while the electrons are revolving around the nucleus in certain circular path. Next we'll be talking about the atomic number, or the number that particular called as the number of positive charges which is being carried by the nucleus of an atom. This atomic number is denoted by symbol Z. So we can say this is nothing but the number of protons or the number of the electrons which are present in an atom. While if you make the sum of the number of protons and the neutrons, we get the mass number which is denoted by symbol A. So that is equals to the number of protons plus number of the neutrons. Now depending on the number of protons and electrons and neutrons, there are different types of the isomerisms possible. The first of all, let us talk about the isotopes. When I talk about the isotopes, these are the atoms of the same element which are having same atomic number, that's Z, but the different mass number, that is A. So in short, the isotopes have the same number of protons and electrons, but the different number of the neutrons, and hence their mass number, that is A, becomes different. For example, if I talk about hydrogen, hydrogen exists in three isotopic form: the hydrogen, deuterium and tritium. Their atomic numbers, that will be 1, but since they have different neutrons, for example the hydrogen has 0 neutron, so mass number is 1, deuterium has 1 neutron, so mass number is 2, and tritium has 2 neutrons, so mass number is 3. So they have same atomic numbers but the different mass numbers, so they are called as isotopes of each other. Since they have the same atomic number, they occupy same position in the periodic table, So their chemical properties will be different. Chemical properties will be same. Physical properties will be same except that particular mass. When we talk about the isobars, so the number that is atoms that are having the same mass number this time. So mass number, that is A, it's same, but they have different atomic number. This is possible when they have different number of electrons, protons and neutrons, but the sum of the protons and the neutrons will be same. For example, argon and calcium, they have atomic number different. Argon is 18 and calcium is 20, but both of them have the same mass number, that is 40. Since they have different atomic numbers, they occupy different position in the periodic table, but their chemical and physical property will be different except that particular mass that will be same, that is 40. The next term is isotones. Isotones, when we have the same number of neutrons. So neutron number will be same this time. For example, silicon, phosphorus and sulfur. They have different number of that particular atomic number. For example, silicon is 14, phosphorus is 15 and sulfur is 16. Even their masses are different. Silicon is 30, phosphorus is 31 and sulfur is 32. But all of them have same number of neutrons, that is equals to 16. So they are called as isotones of each other. The next term that we'll be dealing with, that's nothing but isoelectronic species. Isoelectronic species are the atoms, ions or the molecules which are having same number of electrons. So if they have same number of electrons, we can also say they have same number of protons as well. So for example, O2 minus, if I write O2 minus, oxygen atomic number is 8. When I write 2 minus, it gains 2 electrons, so the atomic number becomes 10. Next is F minus, fluorine atomic number is 9. After gaining 1 electron, this also becomes 10. Neon, basically it's 10 only. Then we have sodium atomic number 11, but when I write plus, they have electrons 10. So all these have same number of electrons, so we call them as isoelectronic species. The next term that we'll be dealing with, that is nothing but isosters. The molecules having the same number of atoms and the same number of electrons, we call them as isosters of each other. For example, let's say N2. When I say N2, the number of atoms over here is equals to 2. When I talk about number of electrons, each nitrogen contains 7 electrons. So 7 plus 7, that's equals to 14 electrons are present over here. When I am talking about the carbon monoxide, over here if we talk about it, number of atoms is equals to 2. Carbon is 6 and oxygen is 8 atomic number. So 6 plus 8, that's equals to 14. So here they have same number of atoms as well as same number of electrons. So they are called as isosters of each other. And finally we have a term that is nuclear isomers. The atoms with the same atomic number, same mass number, but the different radioactive properties. For example, if I talk about bromine, bromine exists in 2 nuclear isomeric form. Both of them have the atomic number 35 and mass number 80, but one of them has the half-life period of around 4.4 hours, while the other is having the half-life period of 18 minutes. So they have same atomic number, same mass number, but the different nuclear properties. That's why we call them as nuclear isomers of each other. Now we'll be talking about some of the atomic models. We now just discussed about the different atomic particles in an atom, but how these particles are located in the atom, that we'll be talking with respect to different atomic models. The first ever model, in order to explain the arrangement of these particles in an atom, was given by the J.J. Thomson, called as Thomson's atomic model. According to Thomson's atomic model, the positive charge is spread over the entire sphere, while the negatively charged electrons will be embedded to make the atom as a whole neutral. So it is something like a model where the resins are there in the pudding. So we call this as plum pudding model, or this is also known as a watermelon model. But this watermelon model is not explaining the concept of or the arrangement of the neutron in that particular atomic model. The next most famous atomic model is the Rutherford's atomic model, which is being a result of the scattering experiment of alpha particles by the thin metallic foils. As we know that different observations being made when the thin gold particles, gold foils being bombarded with the alpha radiations. As we know that when this particular alpha radiations being passed or bombarded on these gold particles, some of these radiations easily passed through that particular gold foil, but some got reflected back in the angle of 180, while some got diffracted at the different angles. And all this, on the basis of all this observation, some of the main features of this Rutherford's atomic model have been put forward. So now these main features are, first of all, some of the radiations got deflected at the angle of 180, that is because of extremely small and a dense positively charged particle is present in the middle of the atom, that we call it as nucleus. The nucleus is the heaviest part of that particular atom, and it is extremely small as compared to the size of the atom. Secondly, the nucleus is being surrounded by the negatively charged electrons, and which are having the charge which is balancing the positive charge on that particular nucleus. The electrons are not stationary, obviously. They are revolving around the nucleus at very high speed, just like planets move around the sun. And since most of the radiation passed through that particular atom easily, that's indicating the most of the space inside the atom is empty. The next particular concept that we will be discussing is nothing but electromagnetic radiation. This radiation concept been proposed by the James Maxwell, who suggested that light and the other form of radiation propagates through the space in the form of waves. And these waves are associated with some electric and magnetic radiation. So we call them as electromagnetic radiations. These electric and magnetic field that oscillates in the direction which are perpendicular to each other, as well as to the direction of propagation of light. So we consider the light travels in the space in the form of the wave. Now when we talk about the wave, every wave is associated with some characteristics. First of all, the distance between the two crests or the two trough. So that is, in short, the distance between the two identical points on the wave is denoted by lambda, that's called as wavelength. The wavelength of the radiations is generally measured in terms of Armstrong, and 1 Armstrong is equals to 10⁻⁻10 meter. Number of such waves, when I talk about one wave, we generally consider as one crest and one trough. So number of such waves which are passing at a point in 1 second, we call this as frequency, which is denoted by symbol mu. So frequency is generally measured in hertz. The velocity, that's denoted by symbol c. So velocity is nothing but the distance traveled by that wave in 1 second. So this is distance traveled upon time, that we call it as the velocity of that particular wave. The height of the crest, or you can say height of the trough, denoted by this letter A, that's called as the amplitude, that gives us idea about the intensity or the brightness of the radiation. And we have one more term characteristic related to wave, that's called as a wave number, denoted by mu bar, which is considered as the reverse or a reciprocal of the lambda. It is the number of wavelengths as per the centimeter, or equals to the inverse of the wavelength, which is expressed in the centimeter. Now when we talk about the different electromagnetic radiations, we can arrange them in order of increasing their wavelengths. and such arrangement we call it as electromagnetic spectrum. The complete electromagnetic spectrum, if we talk about the increasing order of frequency, if you talk about increasing order of frequency, it should be in the decreasing order of wavelength, because we know that the frequency is inversely proportional to that particular wavelength. So according to this, if it is increasing order of frequency, there should be decreasing order of wavelength. So order is the different electromagnetic radiations in this order. First we have radio waves, then we have microwaves, then we have IR, that is infrared. Then a region comes, we have a visible region, then we have ultraviolet radiation, then we have X-rays, then we have gamma rays, and finally we have cosmic rays. So these are the increasing order of frequency, and when we have all these electromagnetic radiations together, it looks like a spectrum. So together we call this as electromagnetic spectrum. So right now we are dealing with a word that's called a spectrum. So let us talk about what do you mean by the atomic spectrum. When I talk about a simple white light, if you pass this simple white light through a prism, this light that splits into the different color bands. Now generally if I talk about the rainbow colors, it is something we have a violet, then indigo, then we have a blue, then green, yellow, orange and red. So in short, the simple light, it's split, that we call the dispersion into the different light, and this particular color bands we call them as spectrum. Now this spectrum can be obtained due to two reasons, maybe the radiation emitted or maybe the radiation absorbed, and on the basis of that this atomic spectrum can be classified into two types. The first one, we have the emission spectrum, which is obtained when the radiation emitted from the substance are analyzed with the help of that spectroscope. These spectrum consisting of the lines which are generally of the light color bands, and to observe these light color bands we need a background that has to be the dark one. The particular radiation or spectrum can also be obtained due to the reason of the emission. Now when I am talking absorption, when the continuous electromagnetic radiation is allowed to pass through the gas or a solution, the transmitted light is analyzed. We obtain the spectrum in which the dark lines are observed, and these dark line indicates the radiations of corresponding wavelength have been absorbed. So we call this as absorption spectrum. So as we discussed, the emission spectrum is consisting of generally the light color bands, and to observe them we need a dark background, while in case of absorption spectrum it's consisting of generally the dark lines, and to observe them we need a light color bands. Now we'll talk about the spectrum of the hydrogen, which is being obtained by passing the electric discharge through the gas taken in a discharge tube under pressure. The different lines in the different regions were grouped into the 5 different series, and these all series being named on the basis of the scientist who discovered it. So we have right now total 5 series with us. The first series is the Lyman series. The Lyman series is generally obtained in the region of the ultraviolet region, for which the ground state N1 is 1, and if the ground state is N1, the N2 can have any value on 2, 3 onwards. The next scientist who discovered it is Balmer, whose region observed to be in the visible region, for which the ground state is 2. So obviously the N2, the excited state, can be 3, 4 onwards. The next series is the Paschen series, where it is observed in the IR. Ground state is 3, so 4, 5 onwards is the N2. Next is the bracket. This is also IR. N1 is 4 and N2 is 5, 6 onwards. And last one we have fun, that's also IR. N1 is 5 and N2 is 6, 7 onwards. So wavelength of these different lines can be obtained by a formula, that is 1 upon lambda, that's equals to wave number is equals to R, into 1 upon n1 square minus 1 upon n2 square, where R is called as the Rydberg constant, whose value is fixed to be 109,678 per centimeter. So this is generally we use the formula in order to find out the wavelength of these different lines in the spectrum of the hydrogen. The next atomic model that we'll be discussing is nothing but the Bohr's model of atom. The Bohr has given some of the corrections to the atomic model which was proposed by the Rutherford and the J.J. Thomson. According to this Bohr's atomic model, the nucleus is consisting of positively charged protons as well as the neutrons, but the electron which are revolving around the nucleus, they revolve around the nucleus in certain circular path. We call the circular path as orbit, or we call them as the shells. Now these orbits are associated with the definite energies and hence they are called as energy shells. We can designate them with the letters like K, L, M, N, or we can designate with the numbers like 1, 2, 3, 4 onwards. As long as the electron remains in that particular orbit, it does not lose or gain energy, and therefore these orbits are also known as the stationary orbits. As we go away from the nucleus, the energy level goes on increasing. So K shell is called as a ground state and all other shells are called as the excited state. The energy will be emitted or absorbed only when the electron jumps from one energy level to the other energy level. Only those orbits are permitted in which the angular momentum, which is calculated by mvr, that's equals to n, that's multiple of h upon 2 pi, where m is the mass of the electron, v is the velocity, r is the radius of the orbit, n is the principal quantum number, h is the Planck's constant. So the electron is like other having body moving in a circular path orbit, has the angular momentum that is equals to mvr, and that has to be equals to, or that should be multiple of the h upon 2 pi, then only this particular orbit will be considered. This Bohr's atomic model has main features like it could explain the stability of the atom. The Bohr's model can also give us explanation about the atomic spectrum of the hydrogen, and we also calculate the energy of electron in a particular orbit if it is related to the hydrogen atom or any atom which is consisting of one electron. Now in the case of Bohr's model, we can talk about the energy of electron with the formula energy of any electron is equals to its minus 2 pi square m e raised to 4 z square upon n square h square, where m is the mass of electron, e is the charge on the electron, z is the atomic number, n is the number of shell, and h is the Planck's constant. Since all these values except that z and n are known, we can substitute all these values and we can get the answer of minus 1311.8 z square upon n square. So we can use this formula in order to calculate the energy in terms of kilojoule per mole. We also know that 1 joule is equals to 10 raised to minus 7 earth. So we can convert this particular kilojoule value into the earth value. We get the answer as minus 21.8 into 10 raised to minus 12 z square upon n square. This answer will be in earth, but I am writing this as per atom because this was per mole. So this is being divided by Avogadro's number of 6.023 into 10 raised to 23. We can also calculate the same thing in terms of the electron volt. 1 electron volt is equals to 1.602 into 10 raised to minus 12 or that is equals to 3.83 into 10 raised to minus 23 kilocalories. Hence we can put this value over there and we can express this energy in terms of electron volt as minus 13.6 z square upon n square. This answer will be in electron volt per atom. So these are different formulas in order to calculate the energy. For the MCQ purpose, we need to know this all particular formulas in order to calculate the energy of different orbits. We can also calculate the energy of orbit related to the Bohr's atomic model, from which we have a formula. The radius of any orbit, that's r, is equals to n square h square upon 4 pi square n z e raised, that is e square. If we substitute all these values, that is n is the number of shell, h Planck constant, m is mass of electron, z atomic number, and e is the charge on the electron, we can get a simple formula of r is equals to 0.529 n square upon z, and we can express this in angstrom. The velocity of electron also can be calculated using the Bohr's atomic model, which has been found to be v is equals to 2 pi e square z upon nh. So after substituting all this value, we can get a simple formula of minus 2.19 into 10 raised to 6 z upon n, that is meter per second. So all these formulas we can use for calculating the energies, radius and the velocity of an electron in an atom using Bohr's atomic model. Now we'll be talking about the photoelectric concept, the phenomenon of ejection of that particular electron from the surface of the metal when the light of the suitable frequency which strikes on it, it's called as a photoelectric effect. Now there are different observations we have to remember related to the photoelectric effect. Point number 1, here the light which is having a certain minimum frequency, we call this certain minimum frequency as threshold frequency, which is denoted by mu bar. If this light is having this much amount of frequency, that is only capable of ejecting the electron from the surface. If the light frequency is less than the threshold frequency, then it cannot eject the electron, no matter how long it falls on that particular surface and how intense it is. So in short, the electron ejection concept is totally dependent on the frequency and not the intensity or a time duration for which you expose the metal to that particular light. Secondly, the number of electrons which are ejected, yes, these are directly proportional to the intensity. How intense is a light, that will decide how many electrons will be ejected. Third point, some kinetic energy will be associated with the ejected electron, and this kinetic energy will also be dependent on the frequency and not the intensity. So in short, the photoelectric concept is occurring only when the minimum threshold frequency is associated with the light. Number of electrons ejected will be dependent on the intensity of light, and kinetic energy of electron will be dependent on the frequency of the light. Now in the case of the photoelectric concept, the mathematical concept has been given by the Einstein. According to the Einstein, if the light of energy E, it falls on the metal surface, this energy is divided into two parts. The first one is the work done for the ejection of electron and giving kinetic energy to the ejected electron. So the E, according to the Planck's quantum theory, we can write it as h into nu, that's equals to the minimum energy which is required for the ejection, as we know that minimum frequencies should be threshold frequency, into h, plus the kinetic energy is given is half mv square. So we can take this h mu on that side and we can take h common, so h into mu minus mu 0, that equals to half mv square. This equation is known as the Einstein photoelectric equation for the photoelectric effect. Next we'll be talking about the Planck's quantum theory, which says that the radiation energy is not emitted or absorbed continuously. Rather than that, it is absorbed in the form of small packets. So these small packets of energy, we call them as quanta. Now these quantas are always associated with some energy, and the energies of this particular quanta, it is called as a photon. If this energy is certainly related to the light, we call this as the photon. The amount of energy which is associated with the one photon is directly proportional to the frequency. Therefore, we have E is equals to h into mu. That's called as Planck's quantum equation, where h is a Planck's constant which has constant value of 6.626 into 10 raised to minus 34 joule second. Now a body can emit or absorb energy only in terms of the whole number of multiple of this particular quantum. So we can say E is equals to n into h into mu. So in general, for any electron we can use this quantum theory equation. Now Einstein in 1905 suggested that a dual character of a light, that light can behave like a particle as well as it can behave like a wave. When light is regarded as a wave to explain the phenomenon such as the reflection, refraction, diffraction, but the concept like photoelectric effect, we need to be considered the Einstein's particle behavior for the light. So according to this, the de Broglie also suggested that all material particles in motion which are having certain wavelength, if they are associated with some mass and some velocity, they can also behave like a particle as well as wave. So wave related to that can be given as lambda is equals to h upon m mu. So this is the equation that we can use for the particular equation to find out the wavelength. H is a lambda is the wavelength, h is the Planck's constant, m is the mass of electron, and v is the velocity. So this is de Broglie's equation, which proves that the electron can behave like a particle as well as it can behave like a wave. But according to the Heisenberg's uncertainty principle, it is not possible to measure simultaneously both the position as well as the velocity of the microscopic particle in the motion with absolute accuracy or certainty. So mathematically, the product of uncertainty in the position, that's denoted by delta x, into the uncertainty in the momentum, that's greater or equals to h upon 4 pi. So this uncertainty can be mathematically expressed with this particular formula. So it is to be noted that uncertainty principle is only applicable for the microscopic particle. But actual probability of or actual location of that particular electron, we need to get idea only from the Schrodinger's equation. So Schrödinger incorporated the requirement of the uncertainty principle and the de Broglie concept of the matter wave and proposed a mathematical expression that can express or that can give us idea about the behavior of the electron in an atom. So according to the Schrodinger's equation, or any system of atom or molecule whose energy does not depend on the time, we can write it as the Hamiltonian operator into psi is equals to E into psi. E is the Hamiltonian operator which is considered as the sum of Hamiltonian equation is considered as sum of the kinetic energy operator plus the potential energy operator, where the psi term is very important, which is called as the wave function. We can also write the Schrödinger equation as del square psi upon del x square plus del square psi upon del y square plus del square psi upon del z square plus 8 pi square n upon h square into e minus v psi is equals to 0, where x, y, z are the three space coordinates, m is the mass of the electron, h is the Planck's constant, E is the total energy, and V is the potential energy of the electron. Here the psi is very important, that's express the amplitude of the wave and refer to as the second derivative of the psi with respect to x. Now, if I talk about the physical significance of this wave function, as I discussed, it gives you the amplitude of the wave associated with the electron. and the square of this side, which will give us the idea about the intensity of electron at any point. That is nothing but we'll get idea about the orbitals. That's a three-dimensional space where the probability of finding the electron is maximum. So definitely there's a solution of the Schrödinger equation which giving us idea about the orbital, and it is replacing that concept of orbit which is proposed by the Bohrs. Now if I talk about the chi-square value, if the chi-square value is very high, the probability of finding electron in that place will be very high. While if it is very small, the probability will also become low of finding the electron in that region. So the orbital, this is a new term which we get from the Schrödinger equation as a replacement term for the Bohr's atomic orbit. So orbital, it is the region in the space in which the probability of finding electron is maximum. But if you want to get the exact characteristic of the electron and its location, we need to study the next concept called as quantum numbers. These are the four set of numbers which are step by step gives us idea about the electron and its probability finding in the particular atom. We have four quantum numbers: principal quantum number denoted by symbol N, azimuthal quantum number L, magnetic quantum number M, and the spin quantum number S. Let us talk about the first one, that's a principal quantum number. This gives us idea about the energy shell or a level in which the electron is present. So if I say N is equals to 1, the electron is present in the first shell. If it is 2, it is present in second shell. If it is 3, present in third shell, 4, like that onwards. This also gives us idea about the number of electrons, because if I have to calculate the number of electrons in each shell, that will be equals to 2n square. Now for first shell, this will be 2, for next 8, then it is 18, and then it is 32. So from the principal quantum number, we are not just getting idea about the energy shell in which the electron is located, but we also get idea about the number of electrons which are present in each shell. The next quantum number is the azimuthal quantum number or the angular quantum number, which is denoted by symbol L. Now this L gives us idea about the angular momentum of the electron, and it determines the subshell or the sublevel of that particular principal shell in which the electron belongs. For example, if I have different values of n, 1, 2, 3, 4, then L can have any value from 0 to n minus 1. So for the first, we have only one value, that is 0. For the 2, since it is 2 minus 1 is 1, so 0 to 1, so I can have two values, 0 and 1. For 3, I can have 0, 1, 2. In case of 4, we can have 0, 1, 2, 3. So if I can see over here, we have different values for the different shells. For 1, it is 1, for 2, it is 2, for 3, it is 3, for 4, it is 4. So this gives us idea about the number of subshells for each shell. For example, the first shell is divided into only one subshell, that's 1s. Second shell is divided into two subshells, that is 2s and 2p. Third subshell is divided into three subshells, 3s, 3p, 3d. 4 is divided into four subshells, 4s, 4p, 4d and 4f. Now let us talk about their different values. If I talk about the first shell, over here we can see the value is 0. For the 2s, the value is also 0. For the 3s, the value is also 0. And the 4s, the value is also 0. That means now this subshells and the angular momentum value can be related. If it is S-shaped subshell, the angular momentum value is always 0. Or vice versa, we can say if the angular momentum is 0, the electron belongs to the subshell S. Similarly, for the 2p, we have value 1. For the 3p, we have value 1. For the 4p, we have 1. So for p subshell, it will be 1. Similarly, for the d, it will be 2. And for f, it will be 3. So we can get the answer for the different subshells by just knowing the values of the azimuthal quantum numbers. So azimuthal quantum numbers gives us idea about two things. The first one, the subshells in which the principal shells to which the electron is belong, but also it gives us idea about the number of subshells for each shell. The next one is the magnetic quantum number, which is denoted by symbol m. This is also dependent quantum number because the value of m is totally dependent on the azimuthal quantum number. So let's say if the azimuthal quantum number, we know for s it is 0, for p it is 1, for d it is 2, and for f it is 3. So m can have value from minus L to plus L. So here when I am talking about the s, it can have value only 1, that's 0. P can have minus 1, 0 and plus 1. D can have minus 2, minus 1, 0, plus 1, plus 2. And F can have minus 3, minus 2, minus 1, 0, plus 1, plus 2 and plus 3. Now depending on how many number of the particular values we have for the magnetic quantum number, we can talk about the different orientation. For S there is only one orientation. For the P we have 3 different orientation. For D we have 5 different orientation, and for F we have total 7 different orientation. That is, different shapes of this orbital can be determined with the help of the magnetic quantum number. The next quantum number is the spin quantum number, which is denoted by symbol S. Now the spin quantum number is just giving us idea about the revolving of electron around the atom. The electron revolves when it revolves around the nucleus, it is performing two kinds of motion. I'll give you a simple example of Earth. If the Earth rotates around the Sun, that is called as the orbital motion, and it takes it around 365 days. But if the Earth rotates around itself, that's called a spin motion, and it takes around 24 hours. Similarly, the electron revolving around the nucleus also performing two motion. It's moving around the nucleus, we call this as orbital motion, and it is moving around itself, that's called as a spin motion. So now we are talking about the spin motion of electron. Now this spin also the electron can perform in two different ways. Either it can move in clockwise direction or it can move in anti-clockwise direction. So this spin motion ideas we can get it from the spin quantum number. Now to have this idea, if it is in clockwise manner, we say the spin quantum number that is equals to plus half, and if it is the anti-clockwise, then S will be having value minus half. So magnitude of any spin quantum number, so spin angular momentum of any electron will be decided by the formula S square root of S into S plus 1 into h upon 2 pi. So we get the idea about the spin angular momentum using this particular formula. Next we'll be talking about the different shapes of the orbitals. We have different shapes of orbital, and we'll be talking about different orientations. So just now we have spoken about the magnetic quantum number, which is giving us idea about the different orientation. For the S orbital, we have a spherical shape, that's only one direction, that is non-directional symmetrical structure we can say. Now this is a 1s orbital. If I talk about this 1s and 2s being separated by some empty region where the probability of finding electron is 0, and this empty region we call it as node. So node is the region of the zero probability in case of S orbital. The finding number of node is also simple with the formula n minus 1. So suppose the atom has a 2 shells, so 2 minus 1, there will be 1 node. In case of 1s, 2s and 3s, they are being separated by 2 different nodes. So the S orbitals are spherical, symmetrical and non-directional, and being separated by a region where the probability of finding electron is 0, we call this region as node. Similarly, the P has 3 different orientation. Now these 3 different orientations are Px, Py and Pz. and these orientations are mutually perpendicular to each other. These orbital consisting of two lobes symmetrically about the particular axis and has a dumbbell shape. Now if you can talk about these two lobes are being separated by a plane which is having the zero probability, and this certain plane where the probability of finding electron is zero, we call this as the nodal plane. So like in case of s orbital we have a node, for the p orbital we have a nodal plane where the probability of finding electron is zero. In case of d orbitals we have 5 different orientation. All these 5 different orientation, out of that there are 3 different orientations which lie in between the axes. For example, this is lying between x and y, so we call this as dxy, this is dyz, and this is dxz. While the 4 lobes can also lie on the axis, so we call this as dx square minus y square, and the one which is having all 4 lobes on one z axis, we call this as dz square. Now in case of the d orbitals also we have different planes where the probability of finding electron will be 0. Now when I am talking about the term node and nodal plane, first of all, the node is the region or the positions where the radial wave functions passes through a 0, or probability of finding electron at that point will be 0. If I have to find the number of nodes in any particular atom, we have formula n minus L minus 1. N is the principal quantum number, L is the azimuthal quantum number. For example, if you have an orbital 1s, for 1s we have n is equals to 1, L is equals to 0, and this is minus 1, so that is equal to number of nodes will be equals to 0. If you have 2s, so n will be equals to 2 minus 1 minus 1, so that is also that will be equals to 1. Number of nodes, if I have 2, that is azimuthal number for that particular this thing will be 0, and this will be equals to 1. So now in case, this will be plus 1, so that is equals to plus 1. So when I am talking about this particular number, we get a different nodal planes in this case. Now in case of the nodal planes will be the probability where the probability of finding the electron will be 0, but that will be along the along the axis it will be. Now in the case of this, in order to find out the nodal planes, we have a formula that's equals to the L, that is azimuthal quantum number. So if suppose the orbital is S, the angular nodes will be 0. If it is P, that will be 1. If it is D, that will be equals to 2, and if it is F, that will be equals to 3. So the number of nodes and the nodal plane can be calculated with respect to this. Now we'll be talking about the nodes and the nodal planes. When I'm talking about the nodes, these are the position where the radial wave function passes through the 0, or the probability of finding the electron at that point is 0. So number of nodes, if we have to calculate, that will be equals to n minus L minus 1. N is the principal quantum number, L is the azimuthal quantum number. For example, if we have orbital 1s, for 1s orbital n will be equals to 1. For s, we always have azimuthal quantum number 0, and minus 1, that is equals to 0. In case of 2s, we have principal quantum number 2, but the azimuthal is again 0, minus 1, that will equals to 1. So in this way we can calculate the different nodes for the different orbital. In case of nodal planes, these are again the plane where the probability of finding electron will be 0. In case of nodal planes, if you have to find out the number of nodal plane, the formula will be equals to L. So for s orbital, nodal plane will be 1. For p orbital, nodal plane will, s will be 0, nodal p 1, d will be 2, and f will be equals to 3. In case of next part, that is electronic configuration of an atom, it is generally the distribution of electron in different shells or in subshells. But if we have to distribute electrons, we are having lots of different orbitals with us. Exactly where to start to have that idea? The first rule given by the above, that's called as above principle, which states that the ground state of an atom or an electron enters the orbital having the lowest energy first, and subsequent electrons are then fed in order to increasing energies. Now in this case, if I have to find out the energies, now I have different orbitals but I am not aware of their energies. Now these energies can be calculated with the formula, that's N plus L rule. This N plus L rule says that the principal and the azimuthal quantum number total, if it is lowest, then the energy of that particular atom will also be the lowest. For example, if I talk about the 1s orbital, then for 1s orbital, principal quantum number is 1 and azimuthal is 0, so that's equals to 1. For the 2s, the principal quantum number is 2, azimuthal is 0, so that's equals to 2. So now if I talk about 1s has the low value of n plus L value, while 2s has the more value of n plus L. So that's indicating 1s has lowest energy and then 2s. And because of this, we can put the electron in 1s first and then electron goes in 2s. Similarly, then it goes in 2p, then it 3s, then it goes in 3p, then it goes in 4s. Then it goes in 3d, then it is 4p. Now in case of 3d and in case of 4s, 3 has a principal quantum number 3 and d has principal quantum number 2. So that's equals to 5. And in case of this, it's 4 plus 0, that's equals to 4. And that's why if I talk about it, though the 3D comes first and then 4s, but while filling the electron goes in 4s first and then it goes in 3D. So these are the different energy level which we have decided to fill according to the principal quantum, that is Abou's principle, in order to fill the electrons. The next is a Pauli's exclusion principle, which says that no two electrons in the same orbital can have the same number of quantum numbers or a same set of quantum numbers. For example, let us talk about the helium, which has atomic number of 2. So now if I talk about the electronic configuration, it will be 1s2. Let us talk about, we have 2 electrons here. Now this is first electron of helium and this is the second electron of helium. Now if I talk about its principal quantum number, that's 1 because both are in first shell only. Both are in s orbital, so both have 0 azimuthal quantum number. M can have value from minus L to plus L, so this will also be 0. And now if I talk about spin quantum number, for the first, that's odd number electron, it will be plus half, and for the even number of electron, it will be minus half. So now we can see, though the 3 quantum numbers are matching, but the fourth set of quantum number is different. If suppose, if I say the third electron if the helium has, and if I put that third electron in this 1s only, then it will have first N1, L0, M0, and since it is odd number of electron, it can have value of spin quantum number plus half. If I see the quantum numbers of third electron are perfectly matching with the first electron, and because of this reason, according to the Pauli's principle, you cannot put more than 2 electrons in one orbital, because if you put the third electron in the same orbital, then it will have the same set of quantum numbers, which is not possible according to the Pauli's exclusion principle. The next principle is the Hund's rule of maximum multiplicity, where it says that when you are filling the electrons in case of P, which has 3 orbital, in case of D, which is 5 orbital, and in case of F, where it has 7 orbitals. If you want to fill electrons over here, the pairing will take place only when if each orbital is filled with 1 electron each, and then the pairing will start. So you have to fill 1 electron in each orbital, then only the pairing will start. If you pair the electron first, the energy gap between the 2 electrons will increase and filling the electron in the next orbital will become difficult. Hence, it is always suggested according to the Hund's rule that pairing will not occur unless and until each orbital is filled with 1 electron each. So So using all these principles, we can write the electronic configuration of the different elements. For example, if I have a sodium, it's 11. So according to the electronic configuration, let me put first of all the above diagram in front of you, so that will be helpful for you in order to find out the how to fill the electrons over here. First of all, according to the above diagram, the electron will go in 1s first. S has a capacity of 2 electron, so this will be 1s2, then 2s2, then it will go in 2p. Its 2p has a capacity of 6 electron, then it will go in 3s. But we have already filled 10 electrons over here, and we have to fill total 11, so only 1 electron will go in s orbital. Similarly, for the chlorine with atomic number 17, it's 1s2, 2s2, 2p6, 3s2, and now 3p5, that is 17 electrons. For the scandium, it's 1s2, 2s2, 2p6, 3s2, 3p6. Now electron going in 4s, 4s2, and then 3d1. Next, 1s2, 2s2, 2p6, 3s2, 3p6. You just count the electrons in between. So these are 10 electrons. Then after 3p, electron goes in 4s2. So this is 20 electrons we have completed. Then it goes in 3d, 10, 30 electrons done. 4p6, 5s2, 4d10, 5p6, 6s2, and 4f2. So this is the electronic configuration of cerium. So we can see 10 plus 10, 20 plus 30, 36, 38, 48, 48 plus 6, that is 54, 54 plus 2, that is 56, and plus 2, 58. So this way we can write the electronic configuration of different elements.